high frequency waves hitting the eardrum, it's going to produce very high frequency waves in the scala vestibular. Now, if you have a very low frequency vibration in the stabies and in the oval window, it's going to cause very low frequency waves moving through that liquid's parallel to the scala vestibular. But those low frequency waves will travel farther through the snail's comb. That makes sense so far? Now, we haven't talked about the round window much. The round window is very important for pressure regulation in the cochlea. So the round window is exactly like the oval window, a very thin, flexible piece of connective tissue. If we remove the round window, we just had bone here, and then we cause this vibration to hit this little oval window. Think about trying to, I guess I always use my pop can example. If you had a pop can and you tried to squeeze it, what would happen if it was closed? An open can of soda. I mean, unless you were like that guy on Game of Thrones when he crushed the guy's skull, you squeeze a pop can, it doesn't move, right? You can't really squeeze it and bust the can open because there's so much hydrostatic pressure from the fluid inside. This cochlea is filled with fluid. So if it was filled with fluid, and you tried to vibrate that open window, and this was just bone here, what would happen? Nothing. You wouldn't be able to produce a wave, right? Now what if we took a pop can and cut a hole in it, and then let any of the fluid out, and then put like some type of membrane, or a flexible membrane over it? You could squeeze the pop can, and what would happen? That membrane would expand, and fluid would push into there. So you could actually change the shape of that can. So because the round window basically relieves pressure that's generated in the cochlea due to vibration of the oval window. So without this round window, you couldn't produce sound because you wouldn't be able to actually create a wave, right? That's the fluid inside the window. Make sense? Good. All right. I think we're done with our snail. We all have those regions down? Everyone likes the snail drawing? Good. Okay. Now let's get into some more fun terms. Ear anatomy has always been a lot of fun. There's just all sorts of stupid terms. I don't know what they call half these terms anymore, but we'll do it the way I like it. All right. So now we're going to take our cochlea and straighten it out. This will make it easier to understand what's going on. So instead of a snail, we're going to pretend our cochlea is just this large leech-looking thing. Okay. We have our oval window. We have our round window. Have our little blind bony collar here, which from it will be our scala media chamber. So again, we can fill in these chambers, scala media. Scala cutánea, scala vestibular. Okay, so we've stretched out our little cochlea snail, we can flatten them out. So now we can learn a little bit more, and again, we probably should put this as parallel. Make sure our diagrams look good. And when we stretch our snail out, you can definitely now see how those two chambers of parallel, the scala vestibuli and scala cutánea, are actually connected, right, around the scala medium. Should again remember that the outside of this cochlea is calcified, so it's very contacts that oval window. Okay. So it's the same basic drawing, we've just killed our snail and flattened it out. I don't think that'll work in real life, but that's all right. Okay. So this is where we get into some really funny terms that I quite like. Because the scala media, the cavity of the scala media is not actually calcified around it. So this is not calcified. It's just like a snail, it's flexible, right? It's like a soft little organism, so it's a membrane. So it's not calcified, this is really a thin membrane. That's anchored on the vestibuli between the oval window and round window, right? And that little thin membrane is encased around our endolymph. Let's not forget our endolymph. Now this membrane has some very unique terminology, which is always fun. I know everyone likes to learn new terms every day. So we call the portion of the membrane that's on the same side as the scala vestibuli, that contacts the scala vestibuli, we call this Reisner's membrane. Reisner's membrane. And we call the membrane on the side of the scala tympani, we call this one the basilar membrane. Basilar membrane. So it's contacting the paralymph of the scala tympani, whereas the Reisner's membrane, probably named after somebody named Reisner, I don't know, contacts the paralymph of the scala vestibuli. Again, these are thin membranes. Right? Now, it gets a little bit more difficult than that. Because on top of this basilar membrane, I know why it's called the basilar membrane, because this basilar membrane really acts like the basal lamina for a set of cells. Right? So there's little tiny cells that line the internal cavity of the basilar membrane. We'll draw a little nuclei. So we remember that they're little cells. These little cells individually we call hair cells. Hair cells. And we call them hair cells because each little one has cilia. It's important that we get every single cell. I want this to be as accurate as possible. Might make you draw this on a test. I don't want you to get points off and not have cilia on every cell. There's little cilia on every single cell. Now every little cell is called an individual hair cell, but when you term them collectively, these hair cells that aren't epithelial cells, even though they kind of look like epithelial cells because they're lining some type of membrane, collectively these are called the hair cells of Corti, or Corti. Hair cells of Corti. Most of you probably knew that there were some type of little ciliated cells involved with hearing already, because when you have hearing damage, it's oftentimes these little tiny hair cells that are damaged. You'll see how these are important in producing sound here in a minute, or actually converting sound waves into chemical signals. Now, interacting with these little hair cells, all of our one does. We use red, it will not be red. There's a very Tectorial membrane. Tectorial membrane. So that's pretty much all the structures you're going to need to know to figure out how a physical signal is converted into a chemical signal in the ear. All right? So, one more thing about the hair cells, though. It's these little hair cells that actually do the converting. Little tiny cilia are going to move, which causes action potentials to be generated. But not really action potentials. It really creates receptor potentials. So these little tiny hair cells are actually functioning as separate cells. And they actually innervate with neurons, cell bodies of neurons, whose axons help form the auditory neuron, which then travels to the temporal portion of your brain. So these are the separate cells that create receptor potentials that then control action potential generation in auditory neurons. Right? Kind of like how your photoreceptors were the separate cells that picked up light waves in the eyeball and then sent the signals that they were getting to the neurons that eventually form your optic nerve and send that signal to the parietal region. Primary vision is sensitive. So it's the same thing, except now we have hair cells of the organ of Corky. All right. Okay, so how does this all actually work? It's actually pretty simple. I know it's kind of a complicated drawing, but it's really not that difficult. So basically, trying to start from the beginning, the sound wave moves through the ear canal unabated because of the function of our ear canals, glands, and hair. Vibrates the tympanic membrane or the eardrum, causes the hammer to vibrate, causes the anvil to vibrate, causes the stapes to vibrate, which causes the oval window to vibrate. When the oval window vibrates, that will generate waves in the skull vestibule. Right? And when it generates waves in the skull vestibule, moving down the skull vestibule through the parallel, what do you think is going to happen to a very thin membrane that's next to those waves? It's going to cause our Reisner's membrane to vibrate and form a wave-like pattern. So as waves are generated in the scala vestibuli, they cause the Reisner's membrane to form a wave-like pattern because it's a thin membrane adjacent to the scala vestibuli. And when this thing starts waving, the Reisner's membrane starts waving, what's going to happen to this endolymph in the scala medium? It's going to start creating waves, right? Because it's fluid. It's like when you make a wave in the water. Waves carry on, right? So the wave here creates a wave in the Reisner's membrane, which creates a wave of the endolymph inside your scala medium. What's going to happen to a very thin tectorial membrane that's adjacent to the endolymph inside that scala medium? It's also going to take on a wave-like pattern, right? Because of the waves in the scala media that were generated by the Reisner's membrane waving, which were generated by waves in the parallel of the scala vestibule. Right? Makes sense? So that tectorial membrane contacts these little ciliated cells with cilia of these ciliated cells. And when these cilia bend, it creates receptor